Oh, I'm delighted to receive a Kastler Prize. This is a wonderful day for me, and I would like to thank you, Monsieur le Président, and also Frau Professor Zwicknagel for awarding it in such a wonderful way. There are many people I think I should thank, but first of all I would like to thank my wife Uschi, who is sitting here in the first row, for supporting me for my whole career, 44 years, and she gave me advice, she encouraged me. You know, you all know scientists sometimes have a difficult time to get through difficult problems, and she has been wonderful. Thank you so much, Uschi. I'm very grateful for the two selection committees, on the German side and on the French side, for selecting me for this prestigious prize and for recognizing my work. It's really great, and I'm very, very pleased. I should not forget to also thank the people who have been working with me, my students, my postdocs, my colleagues through the years, and I want to say that I really enjoyed to work with them, and we had exciting times, we had wonderful times, and that's also because I sort of was able to collaborate with these people. So today I would like to report on some recent work which we did through the last 3 or 4 years, rather than telling you about a broader scope of my older work. And what it is about is a new theory of the critical properties near a quantum critical point in metals. I would like to first tell you about quantum phase transitions in general. Then I will introduce the new concept of critical quasi-particles, which are fermionic excitations in metals near a quantum critical point. That brings up the question of two kinds of critical degrees of freedom in these systems, namely fermions and bosonic fluctuations. And I'll present a self-consistent theory of these two parts of the system, which has fermion compounds, and I picked the two compounds that have been most well investigated, namely this ytterbium compound and this cerium compound. So, okay. What is a quantum phase transition? Well, we all know thermal phase transitions. A thermal phase transition is a transition from a state of macroscopic order, which is destroyed by thermal fluctuations, and then you get into the disordered or unordered phase. Now, a quantum phase transition is a zero temperature phase transition between distinct ground states, for instance, ordered, magnetically ordered and not ordered, induced by a variation of a non-thermal control parameter, which might be pressure, magnetic field, chemical composition, and so on. Now you might say, well, what about a phase transition at zero temperature? We'll never be able to investigate a phase transition at zero temperature. But that's not the point, because it turns out that this phase transition makes itself felt in a large region of phase space at finite temperature. And typically it looks like here, this would be a metal insulator phase transition as a function of disorder x here. So at this point xc, you would have the transition from metal to insulator, and above that there is a whole region where you get critical behavior, scaling laws and unusual properties, or the very well-known phase diagram of the high TC cuprate superconductors, where you have an antiferromagnetic phase here at small hole doping X, and the superconducting dome here. So there are quantum phase transitions here, 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 and there's also this ominous T star line that signals the pseudo-gap phase here, which might end at a quantum critical point here as well. From a more theoretical point of view, if we have a phase diagram like for an antiferromagnet, as shown here, we have the antiferromagnetic phase in the temperature control parameter plane, then what we have is that there is a temperature, the Néel temperature, Tn, that marks the second order thermal phase transition from the paramagnetic to the antiferromagnetic phase. So you come from here and you go down here as a function of temperature and you get into the antiferromagnetic phase. Now it's well known that near the Néel temperature, spatial fluctuations of the antiferromagnetic regions of size psi, the correlation length, determine the critical behavior. And this correlation length psi diverges as a power of the temperature distance to the Néel temperature. And it's characterized by an exponent, nu, classical in this case, the correlation length exponent. Now at a quantum phase transition like here, the situation is more complicated because near the quantum critical point there are also dynamical quantum fluctuations, which is time-dependent quantum fluctuations of a certain energy. And if this energy, h bar omega fluctuation, is larger than the thermal energy associated with the Néel temperature, then these fluctuations are important and they have to be taken into account in the description of the critical behavior. And since Tn goes to zero at the quantum critical point, you see that you cannot avoid to take into account these time-dependent fluctuations. So then we have a correlation length that diverges as a power law of the distance of the control parameter to the critical value, xc. And in addition, we have an energy scale, omega fluctuation, that goes to zero as a power law of this parameter. And the exponent that governs the characteristic energy is given by the exponent nu of the correlation length and a new exponent z, which is the dynamical critical exponent. So if you want to read more about this, we have a recent review article here in RevMod Phys in 2007 on magnetic phase transition in particular. So the conventional theory of these quantum phase transitions goes like so. You have an order parameter in such a situation, phi, which distinguishes the ordered phase from the disordered phase, and this phi might be a magnetic order parameter, which is a staggered magnetization for the antiferromagnet, the uniform magnetization for the ferromagnet, or for the superconductor, phi would just be the condensate wave function or the energy gap. Okay, then one can set up a Landau-inspired formulation for the partition function. So the partition function is given as a functional integral over the order parameter field of e to the minus free energy over kT, and the free energy has a Landau expansion here. There's a second order term here and a fourth order term. And the second order term triggers the transition because this coefficient of the second order term goes to zero at the transition and becomes negative in the ordered phase. X is here the control parameter, which is temperature. In a quantum phase transition, you have to take into account, as I just explained, the time-dependent fluctuations. So we have to generalize this description. We have to replace the free energy by a time integral over the action S, and the action S is a functional of the space and time dependent order parameter field. Actually, it's imaginary time, but that doesn't really matter. And it depends on the control parameter, pressure, magnetic field, and so on. And you have to add to the free energy here a dynamical part that describes how the dynamics is working in this system. Now, as was discovered in the early works, especially in the seminal work by Hertz in 1976, is that this theory is a phi to the 4 field theory. And a lot is known about phi to the 4 field theories, especially that it has an upper critical dimension, which means if you have a system which has a higher dimension than 4, then you are in a kind of non-interacting or weakly interacting phase, and you can calculate everything. Now, you would say, well, the dimension is 3, and of course we have time also here, so time-space continuum d plus 1, well, that should be 4. That's not so, because the dynamics is not Lorentzian. The relation between the spatial dependence and the time dependence is not linear. Omega is not proportional to q, usually, like in, relativistic theory. But usually, omega is proportional to q to some higher power, which may be q squared or q cubed. For an antiferromagnet, for instance, it's q squared. And this is the dynamical exponent. So omega proportional to q to the power z. Okay? So the effective dimension in this case is not d plus 1, but it's d plus z, the dynamical exponent. And now think of a three-dimensional antiferromagnet. So d would be 3 and z would be 2. So d plus c is 5, and this is greater than 4. So that's why Hertz concluded everything is fine, problem solved. We have a completely correct theory. We can use the Gaussian theory, which is a simple theory. We can calculate everything. Now, comparison with experiments showed that that is often not the case. And the question is why? And the answer is relatively simple. It's not the case if the fermionic excitations in the system, the so-called Landau quasi-particles, develop critical behavior by themselves. This effect is not taken into account in the Hertz theory. So what happens then is the following. The bosonic critical order parameter fluctuations, they couple to the conduction electrons in the metal. This is all about the metal. And they induce critical behavior of the fermionic excitations, and if that critical behavior is strong enough, then we have a scale-dependent effective mass, m star, of these quasi-particles, which diverges. And as I will show you, in the two examples that I will come to at the end, it diverges as a power law of temperature or energy. And this is a very massive effect. This effect acts back on the bosonic spectrum. And the question is, of course, how? And I will present you a phenomenological theory of this feedback, and when we know that, then we can calculate the properties of the coupled bosonic and fermionic degrees of freedom in a self-consistent way, and we get to a strong coupling solution that appears to be in excellent agreement with experimental observation. Of course, if we would be in a situation where the bosonic interactions, this phi to the 4 term in this bosonic theory, are not weak, then we would be not in a good situation, because we would not be able to solve this field theory. But If this term is still weak, this 5 to the 4 term, and but we can present arguments that it is the case, then the theory is controllable, even in the strong coupling domain. Okay, so what we need is some intuition about quasi-particles in metals. Quasi-particles in metals were introduced by Lev Landau in the 1950s, and this was an absolutely essential piece of theory for the description of metals. Before that, it was not clear why Sommerfeld's theory of metals would work. Because in Sommerfeld's theory, the interaction between electrons was neglected. But as you all know, the interaction between electrons in a metal is very strong. It's on the scale of electron volts. Okay. Landau showed why this is circumvented in the real system, and he argued in a very simple way. He said, let's start with the Fermi gas here. We have electron excitations, hole excitations here, and let's assume that they switch on the interaction adiabatically. And then what happens is that an electron acquires a cloud of excitations around it, a cloud of so-called particle hole excitations. It changes its properties, but what is left is again an excitation with particle character. That's the essential thing, and that's a quasi-particle. So these quasi-particles, they can be described by an effective mass, m star, and by an effective interaction, F, and they produce the same properties as you know from the Fermi gas. Namely, specific heat is proportional to temperature, the spin susceptibility is temperature independent, the electrical resistivity, or the temperature part of it, temperature dependent part of it, is proportional to temperature squared. It is useful to introduce another parameter, which is capital Z, which is just the inverse of the effective mass ratio. And what is capital Z? Well, capital Z is the weight under the quasi-particle peak in the spectrum. So you start with the non-interacting system. This is the single particle spectral function. So the spectral function in a non-interacting system is just a delta function peak here. When you switch on the interaction, this delta function peak gets broadened and a background appears. So this is the background here, and this is the broadened delta peak with gamma, and the weight under this peak will be less than 1. It will no longer be 1, it will be less than 1. Okay, now Landau's idea is that you can calculate all the properties of the system by just using this quasi-particle peak. You can renormalize away this background contribution. It just enters the effective mass, it enters the effective interaction between the quasi-particles. Wonderful. Now, what is required for the Fermi liquid idea to be applicable? Well, obviously two things. Namely, Z should be non-zero. We should have a quasi-particle peak. And for the quasi-particles to really establish their energy before they decay, the width should be less than the energy. So this width here should be less than the energy from 0 up here. Okay? Now, let's think about an extreme case where this effective mass and this quasi-particle renormalization is very, very strong. And this is the case of heavy fermion compounds. If you have metallic compounds containing localized spins like cerium, ytterbium, iron, cobalt, or uranium, then these local spins are exchange coupled antiferromagnetically to the conduction electron spins. And that induces the so-called Kondo effect. So you have here the local spin, it's coupled to the conduction electron spins, and then by a very complicated many-body interaction, this system forms a resonance state at a usually relatively low energy, the Kondo temperature, Tk. Spin gets screened, so in the end there's no more spin here, only a complex that is spinless, You can calculate what the quasi-particles do in the neighborhood of this complex. In the neighborhood of this complex, they behave like they would have an effective mass which is very, very large. So the effective mass ratio is T Fermi, which is 10,000 Kelvin, over T Kondo, which may be 10 Kelvin. So this may be a factor of 1,000. If you put these Kondo ions on a lattice, then you basically get the same result. But what you have to keep in mind is that the electrons are now coherently scattered from these Kondo ions, and they form a heavy Fermi liquid below a certain temperature T coherent, which is a little less than T Kondo. And here is an example of this. This is cerium copper 6, and you see here the spin susceptibility as a function of temperature, and this is supposed to be constant, so it's almost constant here, and the effective mass enhancement is 500 here. So it's really a huge enhancement. Now that's not all. In a heavy fermion system, you usually also have interactions between the spins of the quasi-particles. If the local spins are completely screened, they are only quasi-particles, but these quasi-particles have a spin and they will interact. And this will lead to a magnetically ordered state under certain conditions. This ordered state may be destroyed by applying chemical and changing chemical composition, applying pressure, magnetic field, and so on. And one example, very early example here, is the case of cerium copper 6. This is the case I just showed you, doped with gold. So if you start here, zero doping of gold, you have a heavy fermion liquid, which apparently has no ordered state, down to the lowest measurable temperatures at least. Then if you dope with gold at a concentration of 0.1 here, magnetic order, antiferromagnetic order appears, and this is a quantum critical point. At this quantum critical point, the specific heat coefficient, which is specific heat over T, which should be a constant in Fermi liquid theory, like it's here is almost constant, was shown to diverge. Well, they fitted their result to a logarithmic divergence, and this is exactly the case I was talking about. So you now get an effective mass ratio that diverges as temperature goes to zero. So you have critical quasi-particles. So why is that the case? Well, it's the case because we are demanding that this function here should be independent of m star of the renormalization for large Q. So if this term is dominating and these terms are small, you see that 1 over m star cancels here. This is what we want. So that's why we put the 1 over m star here. So f of q is the generalized Landau parameter, and it goes to -1 at the transition here. Then this is disappeared, and we have only an omega term and a q square term here. Okay. So what do we do with this? Well, we have to calculate the self-energy of the electrons. Now, I'm sorry, we'll be a little theoretical, but only for a short while. Then we'll come back to the comparison with experiment. So the self-energy of the quasi-particles here in so-called one-loop approximation would be given by this diagram. So we have an antiferromagnetic spin fluctuation propagator here, which is exchanged, and this is the electron propagator here, running through here. Now it has long been known that if you do this, you observe that this process only works in a very small fraction of the Fermi surface. So imagine this is the Fermi surface, the sphere here. Then what you have to have here, if this energy is on the Fermi surface and this is also supposed to be on the Fermi surface, you have to, and this is a large wave vector q that is exchanged, then you have to go from a point on the Fermi surface by a wave vector q up to another point on the Fermi surface. And that only works in these so-called hot lines. So only in these red marked area on the Fermi surface, this process will contribute. So you will get a self-energy that's highly anisotropic. That's not what we see in experiment. In experiment, we see an effect that is very robust and that will come from all the quasi-particles. Okay, so we thought about how to get a contribution over the whole Fermi surface, and you get it in this, either by introducing impurities. I mean, these systems usually have impurities, and if you have impurity scattering, you can scatter these lines everywhere on the Fermi surface, so you can distribute the critical behavior here all over the Fermi surface. So this was our first formulation of the theory, and more recently we said, okay, let's take two of these fluctuation propagators, one with plus q and one with minus q, so that the total here has small momentum transfer. Okay, if it has small momentum transfer, everything is fine. If we are anywhere on the Fermi surface, we have small momentum transfer, we will always stay on the Fermi surface. It works beautifully. And what is this? So it's a spin propagator, spin. So we have two spins here, and these two spins you can interpret as energy, S dot S. That's the exchange energy. So you have, essentially, you have an exchange energy propagator here. Okay, there are vertex corrections here also. So it's basically a one-loop diagram with an energy fluctuation propagator. And what does this energy fluctuation propagator look like? Well, here is the imaginary part, so the excitation spectrum. It looks similar to what we had before. So there's an omega squared term, there is a q squared term here, there's a control parameter r here, and everything is decorated with a star in the way that I showed you. Now, if you calculate the imaginary part of the self-energy in this way, and then you get from there the real part, you find that the effective mass in this approximation is given by 1 plus something that comes from this diagram, and this is proportional to energy to some power. This power, d is the dimension, is positive. So if d is 3, then it's 3 minus 3 halves. Okay, but this factor is multiplied by a huge factor of m star here, m star to the power 2d plus 1. So this is just coming from all these m stars that are sitting everywhere here. And now you can say, aha, well, I mean, I come from high energies, okay, then I decrease the energy, then this term will become smaller and smaller here, and well, the whole thing will be smaller and smaller, and I end up with such a relationship here. So m star is basically constant, it will not diverge, and there is some correction term here. This is the spin density wave solution that Hertz and others have discussed. And this is the solution that does not explain experiment. However, if you now argue, if we have this self-consistent equation for the effective mass, and we have for some reason already a large effective mass here, for instance, because we have other fluctuations in the system, and I will explain later where they might come from, then this term may be larger than 1 already, and then you have to compare this term and this term, and you can drop the 1. And then you get a self-consistent solution here, which will give you a diverging effective mass with an exponent 1/4 in 3 dimensions and 1/8 in 2 dimensions. So you have quasi-particles beyond the Fermi liquid and obviously new critical behavior. If one looks closer into this, then one can see that the strong coupling and weak coupling fixed points here in this theory, for those of you who are familiar with fixed points, are separated by an unstable fixed point. And so what you need is precursor fluctuations to access the strong coupling regime. So what we then find is at the critical point we have dynamical scaling. We have for the bosons a dynamical exponent which is given by this combination here, which is 4 in 3 dimensions, and 8/3 in 2 dimensions, but it's actually more important to look at the fermions. We have 2 species, remember, bosons and fermions, and the bosons have a different set of critical exponents, and the fermion dynamical exponent is 4/3 in 3 dimensions, 8/7 in 2 dimensions, because the fermionic dimension is always 1. It's only the dimension perpendicular to the Fermi surface. Okay, then you can also discuss the correlation length at t equals 0, which is in the disordered regime, and the control parameter is, for instance, magnetic field, h minus hc. Okay, and you get exponents there. And inside the critical cone, the correlation length diverges as t to the minus 1 over z for the bosons Cb, for the fermions Zf. So it's a little bit like the fractionalized Fermi liquid scenario, but here we are able to calculate the fractionalized properties. So we have explicit results. And what you then find is that the free energy obeys hyperscaling. So it's a function of the control parameter times correlation length to the power 1 over u, correlation length exponent, temperature times psi to the power z, multiplied by the correlation volume here. And the quasi-particle relaxation rate is also scaling dependent in this way, and that is important for the resistivity and for relaxation rates of other types. So let's come to the comparison with experiment. In this compound ytterbium rhodium 2 silicon 2, we have a phase diagram of this type. So temperature versus magnetic field. We have in the corner here an antiferromagnetic ordered phase. There is a huge range of magnetic fields here from, this is in Tesla, from 0.01 Tesla up to 10 Tesla. So over the most part we have Fermi liquid here. So this blue region is Fermi liquid. We have a huge part, a region here of non-Fermi liquid behavior, so where the behavior is governed by these power laws that I explained to you. We have the 3D antiferromagnetic fluctuations here in this corner. It was very difficult to find out what the magnetic fluctuations are in this compound, and that is because rhodium is a neutron absorber. So the usual neutron scattering experiments didn't work so well, but last fall, the group of Colin Broholm, they got sufficiently good data, and they found that up here you have 3D ferromagnetic fluctuations, and down here you have 3D antiferromagnetic fluctuations, well, as far down as they could get, which is about 0.1. Okay, so we work on the assumption that we have 3D antiferromagnetic fluctuations down here, and as you see in the specific heat coefficient here, you get again kind of a logarithmic behavior here up here in this regime, and you get a power law behavior when you get into this regime. And what we find is a very nice fit of the specific heat. So we would predict t to the 3/4, so t to the minus 1/4 for the specific heat coefficient. This is a wonderful fit here. If we, on the Fermi liquid side, we predict this behavior here, which is also nicely seen experimentally. We get a good fit for all the measured quantities. But I'm only showing this one more, and this is the magnetic Grünhausen ratio, which is a ratio of 2 derivatives of the entropy here, derivative with respect to magnetic field and derivative with respect to temperature. So this is also excellent agreement with theory, but what I like best is this behavior, that this Grünhausen ratio has a universal form in the Fermi liquid regime, and it's given by this combination of critical exponents and dimension, which is 1 1/3 in our case, and they measure 0.3. And this is a pretty sensitive quantity, so that also looks good. What about cerium copper-6 doped with gold? Well, there it's known for a long time that this is a regime of quasi-two-dimensional magnetic fluctuations. Let's apply our theory for two-dimensional fluctuations to this case. This was the case where we got the exponent 1/8, so C over T would be T to the minus 1/8. This is a fit of the specific heat coefficient to this law. It's pretty good. So it's not necessarily logarithmic, because the difference between logarithm and such a weak power law is, of course, very small. We get as a prediction here for the dependence on pressure, and I'm showing as a last comparison the dynamical structure factor measured in neutron scattering by Schröder et al. Some time ago, and we find the beautiful scaling behavior here, and this is a fit of the theory to the data, which is also quite convincing, I think. Okay, so let me come to the summary, and let me point out some open questions. So what we did was combining Fermi-liquid theory and concepts and quantum criticality. Quasi-particles can be well defined in certain classes of non-Fermi liquid states. This, I think, is the new thing that we discovered, that if you have a so-called non-Fermi liquid situation, it does not mean that there are no quasi-particles anymore. The quasi-particles still exist, and they may be well defined, and the quasi-particles that we have here are well defined. Of course, when you go to zero energy or temperature, the quasi-particles disappear, because the quasi-particle weight factor will go to zero in the theory that I told you about. So we set up a critical quasi-particle theory which leads to a self-consistent determination of the effective mass. The application to heavy fermion compounds near an antiferromagnetic quantum critical point was done in the following way, that we used the antiferromagnetic spin fluctuations at large q to produce energy fluctuations at small q, and they lead to a momentum-independent critical self-energy, so the same self-energy all over the Fermi surface. The results are in good agreement with experiment in these two cases, and in other cases we have not looked at in such detail. In our theory, the Kondo screening, in these two compounds at least, the Kondo screening appears to be robust across the quantum critical point, and there is no Kondo breakdown as has been hypothesized in other theories, which is not to say that there is no Kondo breakdown ever. I mean, there may be other systems where Kondo breakdown happens. What we are still lacking is a fully microscopic, we have some ideas, fully microscopic derivation of the assumed magnetic fluctuation spectrum. What we have not done is to apply in detail to other compounds near an antiferromagnetic quantum critical point. And of course, it's an open question to apply these ideas to other types of quantum critical points, like superconducting quantum critical points, Pomeranchuk instability, and so on. I want to thank my collaborators, Elihu Abrams and Jörg Schmalian, and I want to thank you for your attention.